Welcome to this IMI Hydronic Engineering webinar. Through this webinar, we're going to be looking at the impacts that HVAC systems have from a relatively high level on building ownership and the costs of operation and the impact of operation. I think to begin with, it's worthwhile understanding what that investment might look like. It's perhaps not as much as you think. But it has a very, very important impact on the way the building runs and through its life cycle. And we'll come to some numbers towards the end that might help support this concept, that it's not really that big an investment. Now, we know that it only accounts for about 20% of the total building investment, and that includes everything. So that's all the equipment, air handling units, fan coils, boilers, chillers, pumps, pressurization, all of these large ticket items. It's only 20% of the building investment, but it usually accounts for about 50% of the building's energy usage. It's quite a considerable amount. And when we consider, if we put that in a wider context, we're talking about 20% of the world's total energy is used in HVAC systems. It's extraordinarily large. So as you can imagine, there's measures being taken to try and change this for the better in a positive way. Building legislation has changed. It's through the enforcement of taxations on buildings. The less efficient your building, the more tax you're likely to pay on your building. They do it through regulation in order to try and drive design best practice of buildings. But it's not only just about the physical parts of the building as well. You have the efficiency of the people in the buildings, and that has a link to thermal comfort, and we need to ensure that that's correct. And I think with regard to building legislation and regulation, the world's changing very quickly. Technology is changing very, very quickly. And I think we have, given the longevity of buildings being in the 25 to 50 year period, we have to make sure that they're fit for the future in order to accommodate some of the changes that are coming. So I think these are three critical points that we need to look at and address. So if we talk first about the legislation part or the certification part or regulation, they're all slightly different in context, but if we take things like the WELL building, BREEAM or LEED, which is part of the Green Building Council network, people are willing to pay more. Indeed, their studies show people are willing to pay up to 30% more for the same building in the same space. So it's worthwhile investing in these certifications. Outside that, you've got something that's slightly bigger and governs in a slightly different way, and this will really depend country to country and perhaps even region to region as to how this is enforced or adopted. The EPBD is an overall guiding directive that is driven by the European Commission that gives us directives on exactly how buildings should be done from a very high level perspective. Clearly underneath these high level perspective there is usually sub-details of different regulatory bodies that will give us guidance on what's the best practice of design to achieve this. But these regulations, they are here and they do exist. So as an example, under the Energy Performance and Buildings Directive, the EPBD, which was refreshed relatively recently at the very end of 2018, it's only about 1 year old, this new revision, there's some critical things that came up, some critical updates that are contained in here that are specifically pointed at HVAC systems. If we look at the way buildings are run, the way buildings are operated and controlled, what they've said is that it's now going to be mandatory for installation and retrofit of building automation and control systems in non-residential buildings. And it's going to be quite a large amount of building stock. It's not just a few buildings here and there. They're talking about any building with an output of over 290 kilowatts by 2025. So depending on how quickly regions and countries adopt these standards, there could be a considerable wave of renovation required or upgrades to renovations required. We're only talking 4 years away here, so even if you're going to be upgrading your building beyond 2025 or close to 2025, there's some considerations that you need to make there. Requirements for the installation of individual room temperature controls. As an example, a thermostatic radiator valve or zone control in buildings. So where you go and do some replacement perhaps of a boiler or a chiller, it might well be that if you don't have any individual room controls in spaces, that it's going to be mandatory that these are dropped in as well. So it's worthwhile considering what these additional costs would look like in the future. Non-residential and residential buildings, this is an interesting one from an operational point of view. When you have a building automation and control system with electronic monitoring, they're going to be exempt from physical inspections of the heating and air conditioning systems. So there's cost saving to be had there with respect to maintenance reports, system reports. Indeed, it can mean your buildings are a lot more efficient, but they're going to be pushing more readily on this. The next one is very interesting because for a long time we've known that buildings don't always operate under full load conditions. It's fair to say that the heat loads or cooling loads required in a building go up and down as the seasonal variations go up and down. But what they're now asking for is not optimization under full load. What they're now asking for is optimization of performance under typical or average part load operating conditions, including dynamic hydraulic balancing. So we're asking for seasonal commissioning here. In order to ascertain that, we need to be able to measure in some capacity, we need to be able to evaluate the system in some way, shape or form to determine what are we trying to optimize, where are we trying to go from, and where are we trying to get to in terms of optimization. So it'll be interesting to see with current building stock what those potentials are and how we need to adapt in systems in order to overcome that. And the last one is I guess linked quite readily to the first. It's reinforced requirements on optimizing the performance of technical building systems. So adding controls and making sure we're making best use of these controls to make them truly smart. For me, truly smart product is something that not only measures and reports, but also changes data to information and is able to act intelligently. And I think that's the big driver as to where this is going to. I also mentioned certification. There's quite a few reports out there that show that tenants seem to be willing to pay more for certified space, be it LEED, BREEAM, Green Building Directive. Each region will have its own leader in that space, but there seems to be some significant evidence that points towards that. And not only is it more in terms of possible revenue stream, but there's clearly a global impact on these certifications, and they really are driving down the total amount of energy consumed in buildings. So they're a worthwhile investment both in terms of return on investment, but also from a green standpoint. These directives and certifications, seem to be really driving some real change in the marketplace. So to understand a little bit about what it is that it can cost you. So if we have about 1 degree of thermal deviation, we tend to be uncomfortable as human beings. We tend to respond. We either feel too hot or too cold, just being 1 degree out from our set point. This has been measured to be around a 5 to 6% reduction in human efficiency when you have these distractions. Noise is considerably higher and probably a more obvious one, but 5 to 6% in efficiency reduction is quite significant when you consider in most buildings 90% of the costs associated with that building are usually the cost of people, the investment in people to do the work. Now, if we work this out pro rata across all the businesses we had in Europe across 2019, it would have meant a loss of around 250 billion pounds, in additional revenue. So it's quite a significant drop. So this small 5 to 6% reduction, just because you have an uncomfortable zone, means that it will have an effect on the overall efficiency of a business. But it doesn't just stop there. We've also got to think about the system efficiency, because that's just an efficiency drop in humans, this 5 to 6%, because they feel uncomfortable, so they're not operating optimally. But neither is your system usually. So when you're too warm in a system by 1 degree Celsius, or too cold in a system by 1 degree Celsius, we have an intrinsic habit of trying to correct things, which makes sense. I feel cold, therefore I will put on a fan heater. I feel too warm, therefore I will open a window. Now, all of these things, through many, many studies we've done, we've found it actually contributes to a very big increase in the overall energy consumption of the system itself, the heating or the cooling system. So 1 degree Celsius translates to around 6 to 11% of the total energy consumption of the plant when you're outside that in a heating system, and between 12 and 18% of the plant energy consumption in a cooling system. So it's a really significant impact. And if we consider that 20% of our energy in buildings is consumed in HVAC systems, this average 6 to 11 or 12 to 18% is very, very significant in terms of the impact it has on our environment and the overall impact of energy consumption. So it's not something that should be taken lightly, being what seems like a very small 1 degree Celsius difference. So that's impacting both the efficiency of the people, but also the overall running costs of the system itself. So in order to make sure we've got this investment right back from the HVAC system, we have to consider 3 things. We need to meet the energy efficient standards, both now and in the future. There's a tax implication as to not doing that. There's additional running costs. There's longevity of the system. So there's things there that we need to do to meet the energy efficiency. We also need to make sure we deliver a good, stable indoor climate. This is the primary reason that we heat and cool buildings, is for our own comfort. The idea is to do that in the most energy efficient way. If we can get these things correct, we can generally get the capex and the opex part right as well. We can get this return on investment to be as strong as possible. But we have to look at the individual parts of the system to understand where we might get this from. So there's no one magic wand, there's no one magic step that will fix all. And with HVAC, particularly in hydronics, it's the same. There's more than one part to this. So the first part might seem quite obvious, but we need to make sure that we get the right amount of power at maximum conditions in a space. For instance, if you have radiators at home, you would want that radiator to be able to put out 100% of its power when it's required. Perhaps when it's a winter's evening and you want to be warm sitting watching TV. You want that radiator to be able to deliver 100% of power. So we need to make sure that we are able to deal with maximum design conditions when it's perhaps -4 outside or lower. We then need to make sure that we control that space. You don't want the room overheating or being too cold. We know that 1 degree deviation in that set point can make us feel uncomfortable, and it has consequences. And what we can find from studies across the globe is actually around 80% of the time, the system is at 50% load or less. In other words, the system is only running At full load, a very, very, very small fraction of the time. Most of the time it's less than 50% load. 80% of the time it's 50% load or less. So we need to make sure we can control in that space. The next part is to make sure that we maintain these conditions. So we need to make sure that the system stays that way over its life cycle. And there's different steps we can take to doing that. So the 3 steps in terms of solutions are: 1, we should balance a system. So the items that you're seeing there are AFC, which we'll come to. It's an automatic flow control product, and a manual balancing valve. So a very traditional way of ensuring that we have the system balanced to deliver 100% of power at all the areas when we need it, should we need it. Now this itself can generate quite considerable amount of savings, around about up to 35% of the system. And even today, for those of you who have heard about balancing, and it's a well-conceived concept in some countries and a well-practiced concept in some countries, we actually tend to find that a lot of buildings historically are not in this space. They're not even well balanced. So there's considerable savings to be had from a relatively simple solution. The next stage is to look at how do we control that? And can we move to more complex without the additional complexity of installation or operation? Can we move to a more definitive solution? So for instance, moving from on-off control, we can save around 7% more when we move to a fully modulating type system. The last one is to maintain. So we've balanced, we've set the maximum design condition, we're now controlling, but we need to maintain. So we know that small deposits in the system, degradation of pipework, build-up of corrosives in the system, or build-up of particulate in the system, it can really start to affect the overall performance of boilers and chillers and pieces of technical equipment like fan coil units. So this can be up to about 9%. So if you imagine not doing one of these 3 things is perhaps something, but the accumulated effect of getting all 3 correct is considerable. So when we talk about balancing here, what are we talking about? We're talking about making sure that these 3 units here, and indeed all of these units, are receiving 100% of design flow. We know that when we deliver 100% of flow, we will get X amount of power from these units that is enough to compensate for the heat losses in the space. When this doesn't happen, there's some typical things that we've had in buildings over quite a few years. This is typically what people will do. So the pumps might be oversized. So you might find that people go and try to change pump sets out at some considerable expense because they believe they're not delivering enough flow. It could be that the pumps have been originally oversized, and because today pumps are a lot more intelligent, they usually have some form of smart control device, be it an iPad or an iPhone or directly from the BMS system, people can ramp the pumps up and down. So they tend to push the pumps to maximum in order to try and maximize the system. But there's some real issues with that. And in fact, in 90% of the installations that we visited, the distribution is more than 150% of the design flow. So they're pushing too much flow into the system to try and ensure that they have 100% of flow everywhere. But the problem they have is not one of total flow. The problem they have is one of flow not being distributed properly in the correct way. Now this has a knock-on effect. Production units start to suffer from poor delta T's. In other words, in a boiler, perhaps the return temperature is increasing at well above 55 degrees Celsius, and the boiler's not allowed to condense. There's a huge amount of efficiency lost in there. But we're also putting things at risk of reducing life cycle. We're running things harder. The pumps are running harder than they need to be. So how much more often will they need to be serviced? Will they last the full cycle of their life? But generally we also have people that are absorbed in terms of time. They go looking for problems, and generally it can be quite hard to diagnose. So they spend a lot of time trying to correct things, and all the time they're making things ever so slightly worse, or perhaps they make it better for a short period of time in certain conditions, but then they find it's out in another set of conditions. So it's quite hard to find a methodology that allows you to diagnose all problems. And sometimes in systems there are just not enough diagnostics in order to be able to do it. But what we're trying to do when we complete this balancing exercise, what we're trying to do is make sure that all of these units get to 100%. Now there's different ways of doing this. This is one methodology of doing it. This is an electronic balancing instrument that allows us to electronically communicate with these two sensors here. These ones you can see 1 and 2. And the idea is that we use this and a methodology. It's not just about the unit itself, but using computerized methodologies to ensure that the system is balanced. Now, by doing this, you're doing two things. One, you're making sure that you have your system at best design conditions and 100% of flow condition to make sure you can possibly get the best out of it. But you're also making sure you perform some diagnostics in the system in such a way that if there is any problems in the system, you can readily identify and correct it. It gives you a methodology for doing that. So it's really important here that you do follow these the principles of balancing, but have a good and organized methodology for doing it. And there's more than one way to do this. As I mentioned before, this is a very traditional balancing valve, the STAD, the world's most sold balancing valve, and it's been around for a very, very long time. It's still very effective in balancing systems. But there's different ways and different technologies that have come to market that allow us to do this in a more automated way or a more simplified way. And indeed, technology like automatic flow control, where we have thermostatic radiator valves and system. We have components within our valves now that automatically allow you to set the flow to 100%. We don't have to go through this process of proportionally balancing like we saw in the previous slide with two sensors. So it allows us to make something that's generally very time consuming and simplify it in a way that more people can apply it in a quicker way. The last way is, I guess, the Rolls Royce of system optimization. So we call them pressure independent balancing and control valves. So this is a product that combines not only balancing valves but also control valves for things like fan coil units, air handling units, heater batteries, radiant panels, all of this kind of thing, in order to give you the absolute best in control and try and maintain that 1 degree Celsius room space. It really is the way to encapsulate best control. But not only that, it allows us to commission systems in a different way that help reduce the overall investment in commissioning time, which is quite considerable. Because again, we don't need to proportionally balance systems, and in fact we can do it all from the front end of BMS systems, where we don't actually need to have people on site physically doing. We can do it from one centralized control head and say we would like the system parameter set to this. So we can do the balancing and control from a remote perspective with respect to site. We also said that we need to understand about how we control the space. So we've balanced our system, we've ensured that we've got 100% of flow, no more, no less, at our terminal units that cope with the full design conditions. What happens when we start to reduce the design conditions, perhaps because we're up to temperature, or indeed we don't need 100% of design flow to the terminal unit, we don't need 100% of load coming from the unit. So there's a group of characteristics here that we call the global circuit characteristic. And not to overcomplicate things, it's about how these components and their characteristics combine to give us a characteristic. And this combined characteristic between the valve's characteristic, the controlled part, this electrically actuated part, and the inherent design of the control valve itself, we can start to look and say, well, how does this all come together, and how does this start to affect our power versus flow? So there's a characteristic that we're trying to maintain. We're trying to control this characteristic. And there's a way to get that so that it is most efficient and delivering the best possible control, depending on your system design conditions. So we have to start taking these things into account and looking at different ways that we can manage this. Now, it's almost virtually impossible to come up with the perfect control valve in its own right. It's all about having a combination of things that corrects these or adapts to these different system conditions that we're going to have over the duration of its life. So we can use products where we have not only this pressure independent balancing control valve. I said earlier, it allows you to do the system balancing in a dynamic way, in a very simple way. There's no proportional balancing. But more than just that, when you have something like a balancing and control valve, you also need to control it in a specific way, and being able to control the characteristic of how that actuator controls the valve is also critical. So we can do this today in a very digital way. We can do it in a very connected way. We can do it via different bus systems. Indeed, we can set the intelligence in the actuator itself. It's decentralized intelligence, if you like. And things like diagnostics in actuator, diagnostics of the valve in the actuator, being able to identify different parameters and do diagnostics when and if you do have problems in the future is equally as critical as looking at things and during the commissioning phases. So there's different ways we can do this. So we need to take the control part very seriously and not only look at it as the EPBD would give some reference to, we need to look at it outside full design conditions. And using more new technology like this can really help us define what those measurements are, do the diagnostics, and make sure we do optimize the system in the best possible way. The third part of our journey there was to do with maintenance and maintaining the investment we've got here. What we really mean is maintaining the system. Systems will degrade over time. By how much is down to the devices we use or the regimes or the cleanings that we put in place. By default, they will corrode. For instance, if it's a carbon steel or a steel type system, you will naturally get some corrosion. You'll get flash corrosion from the instant you put water into the system. The rate at which that decreases, or the rate at which the corrosion can increase, really depends on many components in the system. It could be diffusion of oxygen in through membranes and expansion vessels, or perhaps air vents that are open that are pulling air back in through. So there's many places that this can, or causes of this, but the purpose of this isn't really to identify all of those different causes, just really to show you here that what seems like a very small change in system condition can mean actually quite a lot in terms of the overall running of the system. So if we take a clean pipe, as I said, you'll get a very instantaneous flash rust, and it will be 0.05 of a millimeter. It's a very, very small amount of corrosion on the surface. But as you can see, as the rust starts to increase here, as we get to this sort of mustard coloured line, and then this orange colour line, and then this heavy rust, we're only talking about 1 millimeter on the overall surface of the pipe internally, which may not sound like a lot. But actually that can mean an increased pressure loss of around 125 to 170%, which is actually quite enormous. Now typically people will try to rectify that situation. Perhaps you don't get 100% of power at all your terminal units. The pump doesn't have enough capability to deliver all that flow against this new resistance in the system. So it's important that we take care of the water quality, and we can use things like air separators and dirt separators to remove particulate that's perhaps already in the system, and air separation to help remove dissolved gases or free floating gases that are in the system as well, to help prevent that corrosion. So there's some clear steps that we can take in order to make sure we take this particulate out of the system and do the best we possibly can to minimize any of these increases in pressure losses. The second part of the maintenance is about maintaining static pressure. So static pressure is similar to when you inflate a balloon or a car tire. It's just there to provide a minimum point of pressure before the pumps begin. So there's a relationship between the pressure, static pressure, and the dynamic pressure that a pump creates. And at different points in the system, you will get variants of this. Now, the idea behind static pressure is we're there to maintain it to prevent two things. One, we're there to prevent cavitation. So cavitation is something that occurs as the static pressure starts to drop, and it drops below the vaporization pressure of the fluid. So let's assume that it's just water in your system. When it drops below that vaporization point, you get these very, very small microbubbles that implode. And what you can see down here on the bottom left is the inside of a balancing valve after it's suffered from cavitation. So these small implosions that happen are literally powerful enough to start degrading and breaking down the metal bonds on the surface of the material. And over time, you end up with material being removed. It's quite common for people to associate this with pump impellers because they create usually the largest pressure drop in the system. But indeed, it can happen in any component that creates a pressure drop. So we have to take care that we maintain a good static pressure in the system. But there's a secondary benefit to it as well. And it can also help prevent air ingress into the system because you keep the system pressure higher than the pressure outside. It can help prevent air coming back into the system, and it can also help reduce the amount of dissolved gases that are in the system. Dissolved gases can and will generally come out into solution at some point, but we can control that. We can control that by using devices that have inbuilt air separation. And today there is no reason why we shouldn't do that. They're as cost effective to procure as a standard system was 5 or 10 years ago. When you start to get air building up, it's not just about the corrosion effect, but you can see from here, fact number 18, air build-up in radiators can massively reduce the amount of power output by a radiator. You just don't get the thermal heat transfer from the fluid, the medium, the water, to the panel, to the air. The air cushion inside the panel causes this massive reduction in power output and thermal efficiency. So it's important that we make sure we don't allow air build-up in the three conditions that we should try and achieve. First one being we trying to make sure the system's optimally balanced and we have no more design flow than required. This is so we can deliver the maximum conditions, the maximum power output when the conditions are required. The second is to control and make sure that we maintain a good, stable and accurate control to prevent overrunning of costs and discomfort of people. And the third part was the maintenance of the system, being able to maintain the system in the design conditions that it was originally set to be in and not allowing them to deteriorate too much. Now, all of these things are intrinsically connected by mechanics, but they should also really be collected by use of data systems, BMS systems, but not only for data amalgamation, but actually making good decision making with regards to optimizing systems, using it for preventative maintenance purposes, and indeed making sure that the longevity of the system is maintained. And all of this, we really believe at IMI that this is something that's intrinsic to a good product. So diagnostics and this connectability to make sure that we maintain these conditions. And you'll find that nearly all of our products are connected through digital connections, through BMS interfaces, or indeed through apps to our phone. So we're able to look at things in a very, very simplistic way from a very high level view in order to help maintain systems. We believe that this is not only part of the future, but really is part of now. And we should take best advantage of using that data and using some of the technical knowledge that we have within IMI to help drive those optimizations and better designs in the future. So I mentioned that there would be some evidence of costing in this as well. So this is a building that we took from the centre of London. It was around 40,000 square metres in size itself, and it was about 100 million in total building investment, so it was a considerable size building. The HVAC system itself was around 17 million for the cost of procurement and installation. Now, when it came to looking at actually the part of the cost of the valves and the water quality, so we're only talking about our steps 1 to 3 here that we've spoken about. There's an approximate cost of around 1.2% of the HVAC solution. So in other words, about 1.2% of the HVAC, the 17 million, is attributable to the valves and the water quality. So what I've actually taken here to make this assumption is the premium product. Actually, it's not a standard balancing valve. I've taken pressure independent balancing and control valves, and I've taken the most advanced water quality investment we can have, and it still only comes to 1.2% of the HVAC. And even more so compared to the overall building cost, it's only about 0.2% of the overall building cost. So the investment is very, very small compared to what could happen if you don't invest in something like this. Indeed, over a 10-year period compared to a standard solution, so still a reasonable solution, but not the premium solution, you would spend 5 to 6 million extra in terms of energy costs in running the building. And if we could take into account the cost of lost productivity with people, and we're assuming there's a 5% deviation here, it's about 6.6% of loss versus the people cost. So in other words, around £6 million per year, £6.6 million per year is lost in productivity, assuming that we're at 1 degree or more deviation in the room space and people are uncomfortable. So it's a considerable amount of money for a very small investment that could be lost. Now, this doesn't include for things, what would it cost me to replace my pump? What would it cost me to replace my boiler or chiller? Or what would it cost me to replace control valves that have cavitated? What would it control? I haven't included for any of that. And not to mention there, but the things like HVAC system failure, so if it's critical plant like hospitals, or even 24/7 hour operation businesses like banks, it's a necessity that these systems have no failures. So we've not taken into account the overall cost of what those failures might look like. Plus, we also have the costs of additional maintenance. So people trying to investigate what problems are, zones that are cold, perhaps areas that aren't getting any heat, or perhaps you're not getting the efficiencies from your chillers that you think you should be having. So there's a mix there that's still not included for in that system. And we really are only talking about a very, very small proportion of the investment here in getting it right. So to come back to one of the earlier slides about maximising the investment, if we can meet all these energy efficiency standards for now, and as far as we can possibly see in the future, we can still do it with a very, very low cost of capex. We know we can do it with equipment that delivers an accurate and stable indoor comfort for all people. And we can then optimize the system to suit those conditions, because we can do it remotely, or we can do it via app or phones or something. We can do it in order to create that perfect indoor environment. And if we get these things right, the capex to OPEX ratio will certainly be good. But most importantly, the return on investment will be as high as it possibly can be, and as well managed as it possibly can be. So I hope you've enjoyed this. If you would like more information, we do a lot of much more in-depth technical seminars on systems with variable solutions, how we control systems, the balancing, and lots of things. I would encourage you to contact your local hydronics engineers from IMI, and you can perhaps go through what your solutions would be in much more detail. Thank you.